While some of the important characteristics of inductors have been presented, there are many more principles which govern their operation and establish their usefulness.
You'll be introduced to the most important of these principles, reactance, in the next video. You can use the information just presented about inductors to understand the operation of a third and final electrical component that finds its usage in AC circuits, the transformer. A transformer is a special type of inductor whose features make it an indispensable component in many electric and electronic circuits. Like capacitors and inductors, transformers are widely used in electronic circuits and communication applications, in addition to electric power circuits. Let's examine the basic operation of a transformer.
You've learned that when AC flows through a coil, a changing magnetic field is generated around the coil. A transformer is made up of two coils in close proximity. If the magnetic field generated by the first coil cuts through the turns of a second coil, an electromagnetic force will be induced in the second coil. This action is known as mutual induction. A transformer only transfers electrical energy from one coil to another by means of a changing magnetic field. Recall that since the magnetic field eventually stops changing in a DC circuit, transformer action cannot take place. Because of this, transformers cannot be used for DC.
Let's take a closer look at how a transformer is constructed.
As the cover is removed from this transformer, you can see the individual coils. Although they are wound very close together, they are neither physically nor electrically connected. They are electromagnetically coupled. The coil to which the AC voltage source is applied is called the primary, identified with the capital letter P. It generates a varying magnetic field, which cuts through the turns of the other coil called the secondary, abbreviated as capital S, and induces a voltage in it. Assuming that all the magnetic lines of force from the primary cut through all the turns of the secondary, the voltage induced in the secondary will depend on the ratio of the number of turns of wire in the secondary winding to that of the primary. This ratio is referred to as the turns ratio of the transformer. This can be stated as the voltage E of the secondary divided by the voltage of the primary equals the number of turns N in the secondary divided by the number of turns in the primary. For example, there are 250 turns on the primary and 500 turns on the secondary. If the primary voltage E sub P is 120 volts AC, what is the secondary voltage E sub S? Rearrange the equation to solve for E sub S equals the number of turns in the secondary divided by the number of turns in the primary times the voltage of the primary. Substituting the values, the voltage of the secondary equals 500 turns divided by 250 turns multiplied by 120 volts. Therefore, the secondary voltage equals 240 volts. From this example, you can see that if there are more turns in the secondary than the primary, then the secondary voltage will be greater or will be stepped up. On the other hand, if the number of turns in the secondary is less than that of the primary, then the voltage will be smaller or stepped down.
Special care must be taken when wiring the transformer into a circuit. If the secondary and primary connections are reversed, severe damage may result. The primary and secondary connections are indicated by markings or by means of a color code. Be sure you know which is which. While the transformer may serve to either step up or step down the voltage between the primary and secondary coils, the actual power that is transmitted from primary to secondary is virtually the same, except for some minor losses with the transformer windings and core.
That is, the purpose of the transformer is to transfer electrical power from one coil to another by electromagnetic induction. It cannot generate or amplify power. Although transformers are not 100% efficient, they are very nearly so. For practical purposes, they are considered 100% efficient. Therefore, the power output equals the power input.
Since the input of the transformer is the primary and the output is the secondary, the relationship becomes the secondary power is equal to the primary power. Since power equals voltage times current, then E sub P times I sub P represents the primary power, and E sub S times I sub S represents the secondary power. If, for example, the primary voltage is 50 volts and the primary current is 2 amperes, then the input power is 100 watts. If the secondary voltage is twice as much as the primary, or 100 volts, then the secondary current must be half the primary current in order to make both sides of the equation equal to 100 watts. The primary current in this example is 2 amperes, so the secondary current must be 1 ampere. So a step-up transformer produces an increase in voltage and a decrease in current, while a step-down transformer produces a decrease in voltage with a corresponding increase in current.
Stop the program and complete activity number 4. When finished, continue watching the program.
Let's stop here and review what you've been shown.